Now we will consider some examples. Okay, the question is find and classify all critical points. Okay. So firstly, our function is x minus 1 squared plus 2y squared. Okay, now, obviously, this is a polynomial, and so it has all orders of partial derivatives, and so all partial derivatives exist of all orders, and they are continuous. Since this is a polynomial. Now, this means, of course, that we can use our theorem for this function, which would be a very simple example at first. So, the critical points are, of course, when the gradient is 0, that is f sub x, which happens to be 2x minus 1 is 0, and f sub y, which is 4y, is 0. So there's only one critical point, and this is x is 1 and y is 0. Okay. Now, of course, we can determine what we have, but let us consider to apply the theorem. So we calculate fxx here. Well, f sub x was this, so fxx would be 2. fyy, okay, this was 4y, so this would be 4. fxy, or fyx, that is, okay, take the derivative with respect to y, this would be 0. So the Hessian would be fxx fyy minus 0 squared. The important thing is it is positive. But also, the second derivatives are positive. Actually, you don't see any x's or y's here because they're always, for all x, they are positive and so on. Okay, but in particular, at the critical point, this holds. And clearly, fxx at p0, well, this should be at p0 for the record. Okay, this is, of course, 2. It's also positive. So together, they say that we have a local minimum at the critical point. Well, obviously, we could see this from the picture right away. Namely, one has, of course, okay, this is our x, this is our y. This is nothing but a paraboloid which is shifted to x equal to 1. So it is like this. And obviously, we have a local minimum, and that is what we obtained. Now, a more serious example is the following. Check. Right. Okay. Now the same argument holds. Being a polynomial, all its partials are polynomials, and so they have all order partials, and they are continuous So theorem is applicable. So to find critical points, we calculate f sub x, which would be 6x squared minus 6xy. That's all. That should be 0. And f sub y, that would be minus 3x squared plus 3y squared minus 12y plus 9. And that should be 0. Okay. Now, to solve such a system, okay, where we don't have just x's and y's of degree 1. We have their products, we have powers, and so on. So this is called a system which is not a linear system. So we don't have just ax or by's, we have more complicated forms. So to solve such non-linear, this means, there are terms which are not just ax or by. There are powers, etc. Substitution is not always a good idea. Because if you substitute, solve for one and substitute, you will have a more complicated formulation. For example, if you solve here, say, for x, you will have a root and so on. When you put it in here, it will be bad looking. So what can one do instead? Instead, one can do the following. Obtain forms like a times b is 0. So a is 0 or b is 0. You will understand what I mean when I start calculation. For the time being, let me give names to these equations. Now, both equations must be satisfied, so we can start from either of them, or we can combine them in a nice way, which will suit our purposes. We will do that step by step. So firstly, by 1, we have factoring 6x, x minus y is 0. So there are two possibilities. Either 6x is 0, that means x is 0, or y is equal to x. We want this equation to be correct, so there's only these two ways. Well, if x is 0, now we still have these two equations. Clearly, one is trivially satisfied because we used one to get this. Now, put this in 2. So, we would obtain, this will go away, x is 0. So we would have y squared minus 4y plus 3 is 0. Now, which means we have two possibilities, actually. If you solve it, y is minus 1 or y is minus 3. Well, looking at this branch, because we started with x equal to 0, now we have y is minus 1, so we get the first point, 0, minus 1. And from here, we get the second point, which is 0, minus 3. On the other hand, in the second case, y is equal to x, we can substitute it in the second one again, because when y is equal to x, the first one is automatically satisfied, because we got it from there, from the first one. So put it in 2 again. To use that information. Well, if y is equal to x, of course, these squares will cancel each other, and this will say y is 3 quarters. Okay. This goes away, you solve for y there. Well, because y is equal to x, we get the point P3, which is 3 over 4 and 3 over 4. There is no other possibility. So these 3 pairs are the solutions. That is, these are the critical points. Okay. So now, we want to obtain, let me see if my enumeration is correct. No, this is not correct, of course. I mean, right. This is y minus 1 and y minus 3, so these are plus. Okay. Well, let us now apply our theorem. Let us do it first with P1, which was 0, 1. Now, to apply the theorem, we need the second derivatives for the Hessian. So, let us calculate fxx. First, we already have f sub x, so differentiate again. That's 12x minus 6y. Well, at P0, that is when x is 0 and y is 1, this is minus 6. Now, we need fyy as well. So let us calculate it from here. That is 6y minus 12. At P0, that is when x is 0 and y is 1, this is minus 6 as well. And we need f sub xy. We could look at either way. So we already have f sub x. Take the derivative with respect to y. That would be minus 6x, which would be the same with the changed order. If you differentiate f sub y with respect to x, you would get the same result. At P0, of course, this is 0. So this says that the Hessian for this point is the product minus 0 squared, so it's positive. On the other hand, f sub y or xx, doesn't matter, at P0 is minus 6, so negative. Together, by the theorem, they say that we have a local maximum at P0. Now for P2, which was 0, 3, okay, I will not calculate these again. I will directly calculate the Hessian. Well, I have this product, okay, but x is 0 and y is 3 now, so it is minus 18 times y is 3, so that's 18 minus 12, which is 6, minus, well, x is 0, so it's negative. Now, Hessian negative says that saddle point. At P3, which is 3/4 and 3/4, that is x is equal to y, the Hessian can be calculated because x and y are equal now. It's simply 6y. Okay? 6y times, these are all products. Right? And fyy, okay, that is, what do we get? Putting 3/4, 18. Let me see, we put 3/4, right, over 4 minus 12. Okay. And minus 6, that is, yes, minus 6 times 3/4 squared. You can simplify this, of course, because we are only interested in this sign. So this would be minus, what should we get here? This would be, if you take 6 square out, for simplicity, that would be 3/4, and this would be 3/4 minus 2, right? So 3/4 minus 2, taking, okay, 6 out, minus 9/16. Now, what does this say? This is 9/16. So this is not important for us. 9/16 cancels with this. So you end up with minus 6/4 times 36. Which is 3/2, 36, so that would be highly negative. So it's again a saddle point. Okay. All right. Let me check with my results. Yes. These are saddles, and this is a local maximum. Okay. As a third, again, a slightly complicated example, let us look at fxy, question being the same, x to the 4th, y to the 4th, minus 2x squared plus 4xy and minus 2y squared. Okay. Now the derivatives, that's to find critical points, we have to calculate and solve the equations. This would be 4x cubed minus 4x plus 4y. Okay, that should be 0. F sub y, to get a critical point, would give us 4y cubed plus 4x minus 4y, and that should be 0 again. Now, to solve this system, okay, we want to bring it into a product form, but you can easily see that these cancel each other if we add these equations. So 1 plus 2 gives that we have 4x cubed plus y cubed equal to 0. Okay. Well, this says that. Okay. Taking y1 to the other side and taking the root, this says y is minus x. Okay. Because the other side is 0. Well, now we can put this in either 1 or 2, because to obtain this result, we used both equations, which means that by putting this into these equations, we will get something new, but not two new things, just one new thing. Okay? So substitute say in 1, in this one, y is minus x, so we have 4x cubed. Well, minus 4x, and y is minus x, so we get this. Well, this of course says that, canceling 4's, x cubed would be 2x, so x is 0, or plus minus root 2. Now, knowing that we already had y is minus x, this means that I have 3 points, and these points are, let me do it correctly. Okay, P1 is 0, 0, because y is minus x. P2 happens to be square root 2 and minus square root of 2, and P3 happens to be minus square root of 2 and square root of 2. Okay. Now the question is to classify these points. To this end, we calculate the Hessian. So x is here, so f sub xx would be 12x squared minus 4. F sub yy would be 12y squared minus 4. And fxy, which is the same as fyx, would be taking the derivative with respect to x here, which would be just 4. Okay. So now let us start with the point P2. We will see the reasons in a minute. This is root 2 minus root 2. The Hessian at P2, okay, that is, you plug in x and y equal to root 2 or minus root 2, but you square them. So x squared will be 2, y squared will be 2, which means both are 20s. Which of course is positive. And okay, fxx at P2, that is, this one is 20. It is positive, so this says we have a local minimum point at P2. Now for P3. Okay. Well, nothing changed because in the Hessian, we use only squares, so they are the same. So similar to P2 case, Hessian would be 20 squared minus 4 squared positive, and fxx would be 12 times 2 minus 4 positive. So this is a local minimum likewise. So we have 2 local minima. Let us consider now P1. Well, at P1, both x and y are zeros, so fxx and fyy are minus 4s. So the Hessian would be minus 4 minus 4 minus 4 squared, which is 0. So this tells us nothing. Namely, we cannot use the theorem. The theorem says something if the Hessian is negative or positive. Doesn't say anything if Hessian is 0. So theorem, okay, does not give any information. Well, this does not mean we don't have a local minimum or a local maximum or saddle point, whatever. Okay. So we have to look from a different point of view. So we can directly look at the function itself. Well, what was the function? It was x to the fourth, y to the fourth, and then it was minus 2. Now, let me put this in parentheses. What remains is x squared minus 2xy plus y squared. But that is x minus y squared. There. Now, after this observation, okay, we have one hint here. Namely, if x is equal to y, if we approach the point 0, 0 from the line x equal to y, this term will vanish. And the rest will be positive. Well, so, okay, as xy approaches 0, 0, on the line y equal to x, okay, f xy, but y is x, would be 2x to the fourth, which is always non-negative. And f p0, or p1, is of course 0. Put zeros here. Well, which means that on this line, f0, 0 is smaller than any other value. Well, this is the definition of local maximum. Okay. So, on y equal to x, f has a local maximum at 0, 0. Because the value at 0, 0 is the, just the opposite, of course, local minimum. Okay, because the value is the smallest possible one among these. So that says all values are bigger than the value at 0, and so it's a local minimum value. Okay. But this does not say f itself has a local minimum, because we restrict it to y equal to x. What happens on other directions? There are infinitely many others. So, okay, let us consider a different one, not y equal to x. For example, okay, we can consider, well, one of them is 0. So, consider, okay, xy approach 0, 0 on, okay, say the x-axis or y-axis. So y is 0. Then f of xy, where of course y is 0, would be x to the fourth minus 2x squared. Now, if x is near enough to 0, that is, in a small disk around 0, 0, okay, so on a small, okay, interval, say, but actually it's not an interval, but it's okay, because we are talking about x, okay, we have x squared minus 2 negative, because x goes to 0. Okay. And f0, 0 is 0. What does this tell us? Well, for very near values, near 0, 0, but on this curve, on the x-axis, the function values are negative. But at 0, it is 0. So this is the biggest value for nearby points. For nearby points. But of course, on x-axis. Okay. So what does this tell us? It tells us that as xy moves to 0, 0 on x-axis, okay, f has a local maximum at 0, 0. Okay. Because all the other values are negative, this is the biggest value. So it's a local maximum. Okay. Conclusion. Okay. On some directions, f has a local minimum. On some others, it has a local maximum. Just two of them are enough. So f has local maximum or local minimum, okay, at least in two different directions. So, okay, P1 is a saddle point. So this example says that the theorem, even though it's quite powerful, does not answer everything. In some cases, it's helpless. We have to go back to the source to look at the function itself in more detail. Okay, the result is not guaranteed, but in some cases we can get a result from there, as this example shows. Okay. Our next topic is an extension of this fact, that is not classifying critical points, but finding minimum maximum values of functions of two variables in some domain, a closed and bounded set, and f will be continuous. So minimum maximum values will exist, but how can we find them? As in the case of one variable, it's not easy in general, but if f is differentiable, well, this is not bad. We can do something there. Well, before starting, let us see that even in one variable case, okay, if we don't have any restrictions, if we are looking for the minimum maximum values of the function on the whole real axis, okay, if these occur at some point, then it must be a local minimum or a maximum. So we have to check these critical points directly. So without restriction, if f from R to R has a local, has a maximum or minimum, okay, it will be, or it will automatically be a local maximum or local minimum. Well, you can have lots of examples. For example, consider, okay, a nice differentiable curve. Y is what e to the minus x squared, for example. Okay. Then this point will be 1. And this is a maximum value. But of course, it's a local maximum value. Okay. The same is true, okay, in the case of functions of two variables. So, similarly, okay, if you have, okay, a function like a hilltop, okay, if this is the maximum value, then it is a local maximum, and so on. Namely, it's the same for a minimum as well. Okay, but this does not yet say that there will be a local maximum or there will be a maximum value. Okay, if you consider the whole plane, a maximum value may not exist or a minimum value may not exist. But if they do, okay, then they will be local maxima or minima. Which means that if this is the case, we can find them. Okay, because they will be critical points. So, okay, in this case, they can be found by finding critical points. Okay. And in this sense, we can use our theorem to classify or whatnot. Okay. And the theorem can be used to classify them. But there is, of course, another possibility if we are not considering the whole real line or the whole plane. Namely, if the domain is restricted by a curve. What happens then? Okay. Okay. But is restricted by a curve. Then the maximum, minimum can occur on this boundary curve. Okay. Now here start the difficulties. Namely, okay, for a function of one variable, okay, the boundary of an interval are just the points A and B at the endpoints. So you check them very easily. But here, the boundary curve has infinitely many points. So it is a little bit more difficult. For example, consider say we have a nice circle here. This is our D. Well, on top of that, okay, depending on the shape of the surface, perhaps we have such a surface piece. Now, what's the largest value? Well, it may happen that the largest value is here, which corresponds to this point. Because unlike dimension 1 case, for such a nice curve, could be a circle, there are no endpoints. Okay? It goes around, comes to the same point. It's a nice, smooth curve. Okay. So at any point, we can have a maximum value. Okay. Which occurs on the boundary. And similarly, the minimum value, somewhere here perhaps, occurs at this point. So for such a surface, the minimum and maximum values cannot be found by finding the critical points of the function, because the minimum maximum values occur on the boundary. So we have some trouble coming in. Okay. Let us consider one example where we can manage it using our previous knowledge. Let us see an example. Okay. Let f of xy be the polynomial x squared plus y squared minus xy plus x plus y, and d be the following. Piece. Okay. Now, firstly, on top of this, what's happening? Well, this is in the xy plane. On top of this, we have the z values, which are given by the function values, and we do not know what happens at the top, where the maximum occurs and so on. Is there a maximum or a minimum? That's, of course, should be the first question to ask. Okay? Well, there is. Okay. Now, since D is bounded, obviously you can put it in a circle, in a disk, okay, and closed because it contains all the boundaries. It's a closed and bounded subset of the plane. And f is continuous. In fact, being a polynomial, it's continuous everywhere. Okay. F has minimum and maximum on D, okay, by the theorem, or if you want, by the extreme value theorem. So there are minimum and maximum values. Where do they occur? Well, they can occur first of all inside D, that is not on the boundary. So they can occur interior, at the interior of D. This means that, okay, without boundaries. Well, in this case, okay, if they occur at an interior point here, Certainly, there is a small disk around it so that it's a maximum. So it's a local maximum, respectively, a local minimum. Then it is local maximum or local minimum. Well, we don't have to decide it right now, but it will be a critical point. Okay, let us find it. Okay, how can we find them? Well, take derivatives, okay? F sub x, which happens to be 2x minus y plus 1. That should be 0. F sub y, which happens to be 2y minus x plus 1, equal to 0. Okay. Well, because you don't have squares or anything or any complications, you can subtract the two from each other, hence get a form a times b is 0. Or you can use direct substitution. This is quite a simple case. So what you get from here, solving, we get p0 minus 1 minus 1. So at this point, this function has a critical point. But of course, we are considering what happens interior of D, inside D. So it is an important question to check if this point is inside D. Well, it is. Okay. Now, this P0 must be checked whether it is indeed. The answer is yes. Because you can easily see that if these are minus 3's, then minus 1, 1 is somewhere here. By any method about the plane you want to use. Okay. Well, you can check that at minus 1, the y value is bigger than this value, and so on. So it is possible to check that. Well, which means this is one of the points we have to take into consideration. And there's only one point. So this is the only critical point, and it is inside D, so we will consider it. Well, the second possibility is boundary of D. Now, what happens if it's on the boundary of D? Well, for this purpose, we observe that the boundary of D, which is a triangle, does not consist of one piece, but 3 pieces, which means we have to look at them one by one. Okay. So let us give names to them. Okay. Call this up to minus 3. Okay. The boundary gamma 1. Call this up to minus 3, the boundary gamma 2, and the last one, gamma 3. Now, these are the boundaries. So we start checking what happens, say, on gamma 1. Now, we can do that because these are straight lines. And gamma 1 is quite simple. Namely, gamma 1 means that the x values are 0. So this is x is 0. But if I say just x is 0, I will be considering the whole y-axis. Okay. Gamma 1 is not that. Y is restricted. And y is between 0 and minus 3. Okay. So what happens to my function then? We are on gamma 1. I can substitute inside the function. Well, because x is 0, when I look at my function up there, I see that I only have y squared plus 1. And not forgetting, Okay, that y is restricted. So now this is an one-dimensional problem. I have a polynomial, I have a closed interval. What are the minimum maximum values? Well, for this, okay, we have to check critical points, which means that the derivative of y squared plus y, 2y plus 1 must be 0. So y is minus half. Okay. Well, x was 0. Together, they say that I get a point 0 minus half. Now, this is a critical point on the boundary gamma 1. I found it by substitution. That is, reducing the function to one variable function. And of course, I have to check endpoints. Well, endpoints mean that y is minus 3 or y is 0. So we get the points for extra, namely P2, 0, minus 3, because x is 0 from the start, we are still here, and P3, okay, where y is 0 as well, so it is 0, 0. So I checked everything I could on gamma 1. Okay. Now let us look at gamma 2. Okay, what is gamma 2? Gamma 2 is just the x-axis. So y is 0 there. But x is not unrestricted. It is between minus 3 and 0. But then, okay, on my function on gamma 2, that is y is 0, okay, simply gives x squared plus x, which is exactly the same problem as in the previous case, but x and y are interchanged. Interval is the same, function is the same, but instead of y, we now use x. This means that we don't have to calculate again. We can directly use the points, changing the places of x and y. So similarly, we get some more points. Okay, we get P4, for example, which is minus 3, 0. Okay. And we get P5, which is minus 1/2, 0. Because y is 0 now, x changes. Okay. And of course, we have x equal to 0. That's also a possibility. Okay. But if x is 0, y is 0, we get the point 0, 0. And if x is 0, it's an endpoint. Okay. We get P3 again. So we don't count it. Okay. Now on gamma 3. Now gamma 3 is a little bit more complicated. Well, not much. Namely, the points on gamma 3 obey the equation of the line, which is not as easy as x is 0 or y is 0. We have to calculate that. It's a line passing through, okay, minus 3, 0, and 0, minus 3. Okay, and so it says that the sum of the terms is always minus 3. In other words, it obeys minus x minus 3. Okay. And, of course, it's not unbounded line. X must be between minus 3 and 0. So we want to check what happens to our function on gamma 3. Well, this is by substitution. Namely, you look at the original function and put minus x minus 3 everywhere in the function, and what you get will be, let me check. Yes, what you get is 3x squared plus 3x plus 2. Okay, so this is what you get. Well, x is between 0 and minus 3, so we look at the derivative for critical points. That is 2x plus 3. We have x squared plus 3x plus 2, which happens to be 2x plus 3. So this implies that x is minus 3 over 2. Okay. Well, if x is minus 3 over 2, y is minus x minus 3, so it makes plus 3 over 2. This is likewise minus 3 over 2 again. So we get another point, a P6 point, which is minus 3 over 2 and minus 3 over 2 from the critical point. Now, when we put x equal to minus 3 or 0, okay, in the function, okay, we get what we had before. Namely, let me see, that's all. Okay. We have, I have my P6, so we would get endpoints minus 3, 0. If you put minus 3 for x, or if you put 0 for x, you get 0 minus 3. These are already found. So there's nothing new in here. All in all, we have 6 points to check. Okay. Absolute maximum and absolute minimum are among these. Okay, actually I said 6, but we have P0 as well, so it's 7 points in all. Well, a tedious calculation says the following. Okay, we calculate f of P0. It happens to be minus 1. And then we have f of P1, okay, which is the same as f of P5, and that is minus 1 over 4. We have f of P2, which is f of P4, and that is 6. And we have f of P3, which is 0, and f of P6, which is minus 3 over 4. Okay. So these calculations tell us that indeed the value which is biggest is 6. So this is absolute maximum of the function on this domain. Okay. On the other hand, the smallest value is certainly minus 1. So this is absolute minimum value. We don't usually write absolute here, but it's the minimum and the maximum values of the function on D. Okay, the minimum value occurs at a critical point, at a local minimum. the maximum value occurs somewhere on the boundary at 2 points. At 2 critical points, that is. So this way, we could find the absolute minimum and absolute maximum values of our function. Now, let us go back and look at this problem. It was tedious, but basically, we solved the problem by substitution. That's to say, on gamma 1, gamma 2, gamma 3, we found the equations, substitute them in the function, and then it became one variable function. And then we did what we knew before, calculated critical points and points, found minimum, maximum values by comparing all the values we found. So, remark is that the basic idea of solution above in the above example was solve x or y on the boundary curves and substitute in f. Thus, make it a function of one variable. So if we can substitute the equation on the boundary inside the function without losing information, that is, as we did here, then we could continue the process because we know everything about one variable functions. Now, the question is, if the boundary curve is given implicitly and we cannot solve it, solve for x or for y. What then? Clearly, this method of solution by substitution completely breaks down because we cannot substitute and reduce the problem to one variable case and then solve it on the boundary. The first part is still intact. That is, well, you have a function of two variables, irrespective of the boundary. You can consider all critical points by finding the derivatives, equating to 0, and solving. Now, an example, let me give you an example here right away, how bad this could be. So this is something like this. For example, consider this. Let D be something as follows. These are 2's, these are 1's, and this is xy cubed plus yx cubed is 9. Does that make sense? If x is 2 and y is 1, you have 8. And x is 2 and y is 1, so it should be 10, I right? So y cube, x is 1, so plus 2 is 10. Okay. So this is the domain in question. What's the problem here? Well, the function is x plus 1. A very simple function, but you cannot solve x or y from here and put it back in here. So there is a problem. Okay. Because it's given implicitly. Obviously, there are 2, 4, 5 pieces in this question as the boundary. But all of the 4 pieces are easy because there x or y is constant. Once you have it, you can easily get this done. Substitution is possible. But on this part of the boundary, which is given by this equation, we have some trouble. Substitution does not work. So what do we do? Okay. Well, a French mathematician with the name of Louis de Lagrange from Napoleonic times, okay, observed that, okay, in such cases, that is, if you have a curve, which is implicitly given, on top of it, if you have the derivative 0, that is, if you have a critical point, if P0 is a critical point, okay, of f, but just above the curve, then, okay, there are 2 vectors which happen to be parallel. Now, this sounds like mystery, but after I explain the method, it will be clear. So what Louis de Lagrange observed is that if you are looking for a critical point on top of a curve on the surface, okay, that's to say the tangent line, okay, will be critical in that sense, then, okay, there are 2 vectors which must be parallel. Now, this important observation led to a method known as the method of Lagrange, which makes calculation quite easy. Otherwise, which could be almost impossible. Okay. By the way, a historic note. Napoleon is a great army leader, a statesman, but less known is that, not less known, but not always mentioned, is that he established 2 universities in Paris. Okay. École Normale Supérieure and École something. Okay. These universities, in these universities, he put all the leading mathematicians, chemists, physicists of France. And thus, France was the most advanced nation scientifically at the time. Well, Napoleon won all of his wars until the last one, the Russian campaign, because his armies could move very fast across rivers because there were engineers, okay, educated in these schools. And they could move over rough terrain because they could build roads, and the French artillery, the guns, when they fired, always hit the target, much more than their adversaries, because they could calculate the orbits mathematically, thanks to Lagrange and the others in the universities. So one of the reasons why he was so successful is that science was on his side. Okay. So what was the method of Lagrange now, which is our concern?